I get ice cream for lunch.
Teacher appreciation day. So Wagner's going to make us ice cream for lunch.
Nice.
Okay, so pretty straightforward. Pretty straightforward. You got one loop. You have 5 milliteslas of magnetic field. The loop area is given to you at point. You don't even have to calculate it. FYI, once again, area has what formula? Geometric formula? Pi r squared. In case you need that, pi r squared. And it turns 90 degrees in 0.1 seconds. So you got your time. Calculate the average EMF. So just plug your numbers in. 1 times 0.2 times 0.005 divided by 0.1. And what is your average EMF? 0.01 volts? 0.01 volts. Okay. Simple, right? Okay.
Mr. Clark?
Yes?
Why no negative and like those
Because it's average EMF. If it was maximum and minimum, your maximum would be a positive EMF and your minimum would be a negative EMF. But we're just looking at the average.
But it wouldn't be the same value, yeah, because it's still creating the same EMF whether it's maximum or minimum. Like in terms of absolute value.
Yes.
Yeah.
Okay, a coil with 45 turns of wire moves in a uniform magnetic field of 1.5 teslas. The plane of the magnetic field is perpendicular to the plane of the coil, which is good. The coil has a cross-sectional area of 0.75 square meters. The coil exits the field in 0.5 seconds. If the coil's resistance is 3 ohms, what is the induced current in the coil? By the way, turns is the phrase that we use for number of wire loops. We say a coil has a number of turns. So this coil has 45 turns. And it's being pulled out of a magnetic field going from 1.5 teslas to 0. So we have a change in B in 0.5 seconds. Well, remember, EMF is equivalent to what? Volts. But it's asking for...
Oh. Got it. Equals IR. Okay.
People do call me that sometimes.
No. What did you get? 33 point something. Why? Because you're finding current. That's fine. Wait, so what do you do? Just multiply by 31? Divide by 5. Oh. I got 33.
So what is the EMF that's produced?
101.25 volts.
101.25 volts. And then V equals IR, defined current, or I equals V over R. So 101 divided by 3 ohms.
Yeah.
And that gives you how much?
33.75.
33.75 amperes.
Oil balls on my shoes.
That's good. Your numbers make sense to me. Okay, so in the first example, what is the change? In the first example, what thing's changing?
It's spinning.
It's spinning. So what in the variable, what in the equation, something in the equation has to change. What in the equation is changing? Area. Okay? So we're going from full flux to no flux. From full area to no area. So it is the area in the first example is changing from area to no area. Make sense? Now in the second example, what's changing? Yeah, we're going from, imagine the screen is a magnetic field. We're going from A to no A. So the area is going from A to no A, or you can think about it as the magnetic field is actually changing. It's going from 1.5 Teslas to no Teslas. Okay? Something has to change. There has to be a change. In the first example, it's A to no A to A. So we have A to no A. In the second example, it's A to no A, or it's 1.5 Teslas to no Teslas. Question?
Does it have to change for there to be like these windows?
There has to be a change for a flux to exist. And a flux must exist for an EMF to exist. Okay.
I'm kind of confused. Same. I don't.
Okay.
The change.
The EMF is the magnetic field's pushback to a change. There has to be a change for the EMF to occur. Okay? You have to upset the oyster for the pearl to be created. You have to upset the magnetic field for the EMF to be created. Okay? So there has to be some kind of change. The flux is basically a change in area or magnetic field. If you change the area from, best example, perpendicular to parallel, then that's a change in flux. If you change the magnetic field to a whole bunch of magnetic field to none, that's a change in flux. And a change in flux gives you a change in EMF. Okay. Make sense? Cool. All right. The thing you've all been waiting for. Transformers. More than meets the eye. Yay! Okay, transformers do something really cool. They are either step up or step down devices. Exactly. When they are step up, they increase the voltage, and when they are step down, they decrease the voltage. So a transformer may step up voltage or step down voltage. But the important thing about a transformer is there's no free energy. Power must be conserved. Remember, what is the formula for power?
Yeah,
E equals IV.
current times.
V equals IV. So the PIV in should equal the PIV out. A transformer has two sets of coils, a primary coil and a secondary coil, that are linked together with what's called a soft magnetic material. Sometimes they just call it soft iron. I'll tell you why soft is important. Sometimes you see transformers equations written as N1 over N2 equals V1 over V2. Sometimes you see it as N1 V2 equals N2 V1. One goes up, the other goes down. And sometimes you see it as NV is a constant. Sorry. But this is the, I don't know what's on your green sheet. I don't know how the College Board wants you to learn it. But this is how it works. The power going into one coil is going to equal the power going into the other coil. And what does Faraday's law tell us about coils? If you increase the coil, you increase the what? The EMF. If you increase the coils, you increase the EMF. So coils and EMF are directly related. They're you double one, you double the other. You triple one, you triple the other. You have one, you have the other. So what you do here is electricity goes in the primary coil and goes around and around and around and around and around. That around and around and around and around creates a magnetic field in the soft iron core. Again, they call it soft iron because it can be easily made into a magnet. Okay? Some materials, hard iron resist magnetic, or hard metals resist magnetic change. Soft metals basically change their magnetic field very, very easily. Paper clips are really easy to make magnets because they're soft. Now, it really doesn't actually mean the hardness of the material, but it does by coincidence for iron. So, the current goes around and around and around and around, creates a magnetic field in the soft iron core. This magnetic field in the soft iron core is translated to this coil. And the magnetic field creates a current in the second coil. But here's the crazy thing. The current going, the EMF going into this coil creates a magnetic field. That magnetic field goes into this coil and creates an EMF out. But if you have more coils, you get more EMF from the same magnetic field. That's Faraday's law. So the same magnetic field that this coil creates, this coil harvests for EMF. EMF in, magnetic field translates, EMF out. By increasing the number of coils, you increase the EMF. That means free power, right? Free energy?
I don't understand.
I'm sorry?
For you.
The number of joules coming out. Remember, power is watts?
Why is it called free?
Free energy basically means energy you can use.
Okay.
That's all it means. It just means energy you can use. The energy available for doing something. So, no, you don't get free energy because whatever power goes in is the same power that comes out. If the current, if the EMF gets stepped up, the current gets stepped down by the exact same amount. If in this case we have 10 times as many coils, the voltage is going to get stepped. The voltage is going to get stepped up by 10, but the current is going to get stepped down by 10. If 1 volt goes in, 10 volts come out. But if 1 amp goes in, how much amp goes out? 0.1. See how that works? That's what a transformer is for. These are transformers. I put one on your desk you can play with. I don't know which one is the in and which one's the out because I just found a box of transformers one day. I'm like, hey, cool, I'll keep those. So basically, voltage and current goes out, and you need at least 2 wires. I don't know why the yellow wire is here. Maybe the yellow wire is like a diagnostic wire. But you need to have current going in, so you need a closed loop, so you have 2 wires. And you have current going out, so you need a closed loop, so you have 2 wires. It might also be red and black is positive, red and black is negative. Red and black is positive, negative for one coil, and red and black is positive, negative for the next coil. I don't know. Maybe next year we'll play with them and actually determine what their turn ratio is, which is actually really easy to find out the turn ratio. All you do is you plug AC on one side and AC on the other side and measure it. Yeah.
Okay, so you said the same amount of voltage goes from one coil to the next, but how is it called like step up and step down if it's the same?
It's not the same, it's the same power. So it's the same power creating the same magnetic field, but the EMF going in and the EMF coming out will be determined by coil ratio.
Oh.
So here we have 10 times as many coils, which means we're going to get 10 times the EMF coming out of this coil, but at the cost of 1/10 the current.
So does it use AC or DC?
And that's the next question. Do they use AC or DC?
Oh.
AC.
Oh.
AC. Why do transformers have to use AC?
Oh, because
Exactly. There has to be a changing magnetic field. There has to be a flux. If there's no changing magnetic field, there's no flux. And if there's no flux, there's no EMF. Does that make sense? So there has to be a changing magnetic field. Now, if you put in some voltage, 1 volt 0, 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 you'll get that changing magnetic field. But if you're going 1 volt 0, 1 volt 0, 1 volt 0, you're really creating not a direct current, but an alternating current. You have to have an alternating current. And here's the cool thing. If you get 60 hertz in, guess what you get out? 60 hertz. Yeah. The change of, basically the flux change in this coil is the same flux change in this coil. So the 100,000 volts that are cruising along the power lines are at 60 hertz. And that 100,000 volts ends up in your house. How does it do it? Well, do I have another? No, I don't have another slide. So there's these big cylinders on poles, and sometimes they're in the ground, sometimes they're in the little green metal boxes, sometimes they're gray metal boxes. Those are the transformers that are taking the 100,000 volts from the dam and turning it into 100 volts that you could use. How do they do it?
Transform.
They do it with transformers. They use 1,000 to 1, or actually a 1 to 1,000 step-down transformer. So the voltage that cruises along the power lines has very high potential, but very small current. And they step the potential down so you can get 110 out of your wall, and the voltage gets stepped down by 1,000, but the current gets stepped up by 1,000. Why is that really useful?
Faster.
Doesn't go faster. Current. Remember we talked about fuses and how when current goes through that little wire, if the current is too high, the wire will melt. If your current is very, very small, that allows your wires to be pretty thin. You can send a lot of current over a lot of energy over a power line and don't have to worry about the wire being all that big because the current is very, very small. The potential is huge, 100,000 volts, 110,000 volts. The current is, or potential is very, very huge, but the current is itty bitty, a couple milliamps. So you don't have to make the wire huge. If you basically wanted to power a bunch of houses at 110 volts and 100 amps, or 30 amps, or 40 amps, what your house will use, the power lines would be the size of buses going into your neighborhood, this gigantic power line going into your neighborhood. That's not useful. Instead, let's crank up the voltage, crank down the current, and use a power line that's about that big, powering your entire neighborhood. One wire, that big.
Yay, transformers.
Hey, transformers, super cool. Yeah, super cool things, these transformers. Okay, how are we doing with this stuff? Is this good?
Yeah.
Okay, questions? Cool, let's do some practice. A 1 to 10 step-up transformer, and again, the ratio is by convention, small number, big number when it's a step up, and big number, small number when it steps down. And what is it stepping? When it talks about a step up or step down, what is it stepping?
Voltage.
Yeah, EMF, or voltage, good. A 1 to 10 step-up transformer requires a secondary coil to have how many more wire coils as the primary coil? 10 times, gotta have 10 times. So 1,000, 10,000. It's probably not 1 to 10 because that one coil would have to be like gigantic to take in all the voltage. But it's probably 1,000, 10,000, 100, 1,000, 500, or sorry, 550. You know what I'm talking about. You know. Stop talking, Mr. Byers. Just let us learn. 110 volts is sent to a 2,000 turn primary coil of your iPad charger. Your iPad doesn't need 110 volts. 5 volts come out. How many turns are in the secondary coil? If you can't do it in your head, you can use the formula. Do you remember the formula? What is the transformer formula?
N1V2 equals N2V1.
Yeah. Or if you like the other way, you can say N1 over N2 equals V1 over V2. V1 over V2. Either one, they both give you the same answer. Depending on if you like to multiply or divide or cross multiply.
Vibes.
It's 2005. Oh. No.
I kind of like that way better. It makes more sense to me. Cross multiply.
90?
90? 0.9 of the coil? What? 91 coils?
Yeah.
91 coils? So yeah, so you're gonna need 91 coils, so you got a 2,000 turn primary coil, grabbing 110 volts, and then a 91 turn secondary coil, which is putting out only 5 volts. Which is good, because if you try to put 110 volts into a DC power supply to power your iPad's gonna blow up. Let's do it. You bring the iPad. What is the resistance of the iPad if it charges at 1.1 amperes? Just a little review. What is the resistance of the iPad if it charges at 1.1 amperes? Which it does, by the way. USB basically is half an amp, 1 amp, or 2 amps.
Stop touching.
And its current incarnation is 0.5 amps, 1 amp, or 1.1. How much? 4.5 ohms?
What volts are you
5 volts.
Ah.
5 volts is coming out of the coil and going into the resistor, which then allows it to charge the iPad. V equals IR. R equals V over I. I divided by 1.1, which is 4.5 ohms. 4.5 ohms, yeah. 4.5 ohms. All right. How are we doing so far? Yeah. Give me a hand, put your hand up and raise whatever if you have a question. If you don't have a question, give me a thumbs up. Ready to move on. Ready to move on. All right. Hey, cool. Lenz's law and flux practice. Okay. So once again, flux is given the letter phi. I don't know why it's given the letter phi. It's just hey, phi is fun. Phi is fun. Phi for flux. Maybe it's just phi for flux. Somebody said even though it's phi, let's say phi for flux. Okay. Change in magnetic induction. EMF change was fine. And there you go. Those are all your formulas spit at you. And again, flux is delta V over delta A. Gotta have delta. And is that it? Oh. I didn't put the practice page in. Okay, so there's practice page missing. All right, cool. So now that you have what you have, you can finish up your lab. Question?
So on that folder right there where it's EMF equals, why on the board is it negative?
Because of the cosine.
Oh,
Because the cosine of the change in cosine makes it a negative value, so it's negative of a negative.
so simply not worrying about it. Yeah.